So this is what's happening this week. We have May 18th to the 22nd. Welcome. The first assignment that's due tomorrow is a Waves Inquiry Stations. I believe there are 4 that you have to choose from. So you pick and you can do a video on that. If you can't do the video, then you can write a script. The next assignment this week is a PhET lab, so that's these both count as labs, so you should do both of these. It's wave boundary interactions. That's the waves on a string sim, and that should give you some ideas of some basics on waves. The next assignment is suggested but not required. That's special wave types. So that's a close reading. So there's a chart in there for you to break down your different paragraphs as well as some sentence frames for comparing, contrasting. And then the last assignment on Friday is what I've been working on for about a week. I know you guys don't think it takes that long, but it does. Is earthquakes. That's due on Friday. And pages 1 and 2 are an assignment, but page 3 is extra credit. I believe that's the challenging part of that assignment. So, and without my being there to help you, I'm not sure that you'll have great success with that. But nevertheless, these are the assignments this week. We have some assignments for next week for waves, and then we're done. I believe Monday, 25th, is 25th a holiday? I believe Monday is Memorial Day, but I'll check that out. So that when I see you on Wednesday, we can talk about that. So today I want to go over the basics of waves. The first idea that we can talk about is, what is a wave? So wave is a wiggle in space or time. And then we have vibrations. A vibration is a wiggle in time. A wave is a wiggle in a place. So it has to be in something. I'm looking for my mark, not my eraser. So this was from one of the videos I tried to videotape last week, and none of them came out so that you could see anything. So I found things online instead, but I did the videotaping. The next thing that you want to know about waves is that it's energy. A wave is energy that's moving. Sometimes pretty much it's categorized as simple harmonic motion. If you've had pre-cal, you might have come across this. I'm not sure if it's pre-cal or if you have to wait to cal to get to the simple harmonic motion. But what is simple harmonic motion? So it's anything that's continuing. It's repetitive. It goes back and forth, like a pendulum that swings back and forth. That's a repetitive motion. The waves in the ocean are repetitive. They come in and they go out. What else is repetitive? Have you ever seen a grandfather's clock? That has a pendulum also that swings back and forth. We use springs in the classroom. So if you hang a weight on the spring, it's going to bounce down and back up again. So all of those are called oscillations. The repetitive motion itself is an oscillation. I want to spell this correctly. I think it's 2 L's. But let me check. Yeah, 2 L's is an oscillation. So we can describe that with the sine wave. So if we have a repetitive motion that's going back and forth like a maybe just a pen on paper, then if we make that paper move over time, then we're going to get a sine wave pictured from that. I'm sorry, I'm not set up well for this today. So let me go ahead and try that and see if we can get a demonstration of that. Here, I have a green marker. I think this one works pretty well. So if I'm moving my hand back and forth and I have paper underneath, I'm just going to get a line that's going up and down, right? Now, let me turn it now. If I'm going back and forth, but the paper moves, we get a sine wave. That color didn't come out so well. Let me see if the orange works better. So I'm moving back and forth, and then I move the page. And I didn't move it smoothly enough at the end, but in the middle, you can see that it comes out like a sine wave. So there are different parts of the sine wave that we want to know about. There's vocabulary involved, and that means that we kind of want to know the anatomy of the sine wave. And like I said, if you've had calculus, you're already familiar with all of this stuff. And if you're in pre-cal, I'm really not sure what that's going to look like for you. Let's see if there's any room left on this one. There's a little bit, but not enough. So the first thing that I want to talk about is where is the equilibrium. So equilibrium is in the middle of the wave. So we draw the wave. I feel like I need a new black one. So that it's happening over time. So on the y-axis, we're going to have height, and on the x-axis is our time. So I've done this line right down the middle because that's where our axis is going to be. That's our equilibrium. So our height is at 0 at that point. Now, let me get some different colors. Purple and blue that work well. I think that's all I have. Oh, I have red too. So now if we want to talk about amplitude, that is the distance from equilibrium to the maximum. So this is our amplitude. But the amplitude does not have to be above equilibrium. It can also be below equilibrium. And here I'll mark that with the capital A. We usually use capital A for that. The next thing that I want to bring up is crest. So this point right at the very top is the crest. And the point at the very bottom, we have bottom one here, is trough. Besides the crest and the trough, we also want to know about wavelength. So wavelength is, we can say it goes from crest to crest. It's the distance from crest to crest. But it doesn't have to be from crest to crest. It can be from any two identical points on the wave. Now, it's easier to go from crest to crest because we can see that that is one complete repetition of the wave. So the wave goes all the way down and it comes all the way back up again. So that's what it takes for one cycle of the wave. Now, if we want to go along the equilibrium, you have to be careful that you're not going from here to here because that's only half of the wavelength. You have to follow it all the way to one complete repetition so that you're meeting an identical place on the wave. It can be from any starting place on the wave. We can start here, but again, we don't just go down and back up again. We have to come back down again so that we've done one complete repetition of the wave. It can be from up high, up low, equilibrium, the very top, the very bottom. But that is one wavelength. That's the distance that the wave travels in one complete repetition. Another thing that we use to describe a wave is frequency. Now, that's not something that I can mark on here. But frequency, this is vocabulary. So we have equilibrium, amplitude, wavelength. Oh, I have to mark this one, wavelength. And the symbol for that is the Greek symbol lambda. So that's the universally accepted symbol. Like I said, for amplitude, it would be capital A. And then frequency. And we also have to describe the period. Frequency is how often it happens. So that's how many oscillations, how many complete patterns per second. So if it takes 3 seconds for one complete pattern, you would have 1 divided by 3 seconds, or that's 0.33 for your frequency. Oh my God. So that's how often the pattern repeats. So we have, I don't want to say revolutions or rotations. It's not always a rotation. I'll just say cycles. Cycles per second. Now, the other term that we have to look at is period. And that's how long it takes. That's the time it takes for one cycle. All right. And then since this is time of the cycle, and this is cycles per second, frequency and period are inverse of each other. So frequency is equal to 1 over the period. The capital tau, so I put the little hats on there, little ridges there. That's the Greek letter that we use to represent period. And the script F is what we use for frequency. So we can also say that the period is equal to 1 over the frequency, because these are inversely, they are inverses of each other. They're inversely proportional. So let me give you some units here. The units of frequency are hertz. So no, I'm not going to put it there. And so again, that is cycles per second. Let's see what else we need to know. Can you see that down at the bottom? Yes, it's still on the video. So let me give you some examples of frequencies. So if we have a bumblebee flaps its wings 130 times a second. That means that it has a frequency of 130, because it has 130 patterns, cycles in every second. That sounds like really a lot, but did you know that a honeybee has a frequency of 225 hertz, or 225 cycles per second? And mosquitoes, we hear that annoying whine that tells us that there's a mosquito nearby. So their frequency is 600 hertz. That's why we get the high-pitched whine. So bumblebees have a frequency of 130 hertz. Honeybees (225 hertz). Mosquitoes are 600. And then if we talk about a radio station, you know how the stations have a number? You dial, maybe you don't, because you probably don't use radio. But I'm an old person, so I use the radio. But you dial it in to a specific number, and that number is actually the frequency. It's in kilohertz. So if we're going to station, let's see, the example I have written down, 960, that's kilohertz. So for the radio, if we can dial it into a frequency of 960 kilohertz, that's going to be that radio station. So that means 960,000 cycles per second, you're getting a signal from them. So what is wave motion? You can think of it as if you see a leaf in a pond and there's a wave going by, maybe a speedboat just went by, then that leaf is going to bob up and down on that wave. It doesn't stream along behind the boat, does it? It doesn't go with the wave. It bobs up and down. If you're at the beach, you can see the what do they call those that bob up and down in the water? Of course, I can't think of it. But it's the energy that is moving along with the wave. So if we have a slinky, we stretch out the slinky, we can shake it up and down, and it goes all the way to one end of the slinky. Maybe it comes back again too. It depends on what you did with the other end. Does the slinky itself go all the way from one end to the other? No, it's the energy. So the energy that we put into that vibration, it's the disturbance along the medium. We call whatever the wave is in, that's the medium. If it's in water, then water is the medium for the wave. So if we're using a slinky, that's the medium. And the slinky doesn't go from one place to another. It's the energy that goes from one place to another. So let me explain that by giving you a few examples of waves. Did you realize that sound is a wave? So if I make a sound, I hit the marker against the whiteboard. Does the marker actually make it all the way to my ear? No, but the marker has vibrated the air molecules that are right around it when when it's being hit against something. And those air molecules, they bump into each other until they make it all the way to your ear. That means the vibration is passed along from one air molecule to the next, to the next, to the next, until it makes it to your ear. So when you have something like construction going on outside, you have big equipment, it's in direct contact with a lot of air molecules, and it's the air molecules, the energy that is put into the air molecules that cause a vibration, and it's that energy that makes it all the way to your ear. So one example is sound, another is light. The sun doesn't make it all the way from where the sun is to our eye, but the energy that it sends makes it all the way to our eye. Sonar is another example. Microwaves, infrared, UV. I'm sure you've heard of ultraviolet. Um, we use those around Halloween sometimes. X-rays, those are all examples of waves. So if you have any questions, go ahead and post those now, but that's it for today. On Wednesday, I'll go over transverse and longitudinal waves, and not sure about Friday, what we'll do on Friday. We'll have to see where we're at. All right. Well, thank you very much and have a good week. Bye bye.